Hello.
All right, let's get started. So as a reminder, I won't be here next Monday or next Wednesday or next Tuesday because it's between Monday and Wednesday. So I posted final exam review. So that's here. It's basically everything that we've done in the semester and stuff that we're gonna get to. We might not get to everything, and so I'll amend this if we end up doing less. But I also posted a sample final, so with 10 questions. I didn't bother posting the multiple choice answers, but the questions are more important because if you can answer the questions, then you should be able to figure out from the list what from the answers which one it is. So any questions about this? Do you want to go over the 10 questions?
Sure. Yes.
Okay. So I was hoping you would say yes to that. So all 10 of these questions appeared on last semester's final. So they really are questions that are representative that you will see on this final. You won't see these questions, obviously, but these are the types of questions that you will see. So first question. So what are methods or ways a user can input a string of characters without spaces? So this is just testing your knowledge of early stuff. So what are the ways that we could input data from the user? Cin is one way, and what's another way? GetLine. Yeah, so those are the two ways. That's all I expect. There technically is another way, but the way we know is Cin and getLine. So what is the type of thing that is returned after applying a logical operator? So what's a logical operator as an example? Yeah, the greater less than stuff. So what's the type of thing that's returned? Yeah, bool. That's it. So look at this code right here. What is the output? Pretty simple to understand. What? So is that X is going to be printed? No. And how do you know that it's not? Condition's not true. Is large going to be printed? Yeah. Why? It's not in curly braces. So I'm trying to get across to you in these questions things that you should do and shouldn't do, but also testing the code. So what should you always do when you have an if statement, for loop, whatever? Use curly braces. Because you will avoid issues like this. Okay, so my friend, I like having questions with my friend in it. So my friend is someone, not really, who's in CSE100 and is just struggling over and over. And so my friend is trying to write a sum of numbers between 1 and n. So if you input 10, I want to sum the numbers between 1 and 10. So the code doesn't compute it correctly. What is the error? So here's integer sum set to 0. N is what some input, doesn't really matter what it is. I have a for loop from 1 to n. Add each one along the way to sum, and then print the sum at the end. So what's the error here? Yeah, it's an off by 1 error. So what is a fix? Yeah, less than or equal to n. So that'd be a fix. So I probably should say what's the error here instead of what's an error. So the theory of errors, I don't know. So here, yeah, the error is that you have an off by 1 error here. So this is getting to more recent stuff. So let's say we have a local variable in a function. How should we return that variable from the function? So what are the 3 ways that we can return anything at all? By value is one way. What are the other 2? By reference and by pointer. So what is one way that we should, should we do all 3 of those, or are there some that we shouldn't do? Well, with pointer, what if I create a variable on the heap using dynamic memory that we've talked about? I'm required to use a pointer there. There's no way around that. So I have to use pointer in some cases. Can I use by value in some cases? Yeah, so that's the way that we have been doing it all along. What about by reference? Why is that an issue? So we create a local variable in a function. Let's just say we have a string function f right here. And let's say we have a string s is hello, and then we return s. So how am I returning the variable in this case? By value. What about by reference? What is the issue here? What is the lifetime of the variable s here? It's within the function, but we're trying to return it, so it's being destroyed when the function's done. And so we're returning a reference to something that doesn't exist anymore. So you shouldn't return by reference. So the answer for question 5, I guess, is by pointer in the case of dynamic memory, or by value in all other cases. Why is using a global variable not a good idea? Yeah, it could be changed by any variable. Is this always true? Exactly. What if I have a constant variable that is a global variable? Is there anything that can go wrong? I can't change it. And so therefore, that value will never change. So there's no issue with having a constant global variable. So it's kind of weird, constant variable. But anyway, in here, I'm assuming that it's non-const. So it's not considered best practice because any function can change the variable. Okay, returning to the horror that is pointers. So let's just say we have an integer y equal to whatever, and I create a pointer of this form to point to y, and then I increment the pointer. Is there an error here? Well, what's the error?
What's the constant? It's the pointer you're trying to change the pointer.
Ah, that's why. So here, is the value of what I'm pointing to constant?
Well, I think that's what the intention was to set the value.
Well, maybe the intention, but is it in this case? No. It's because so read it from the pointer. Yeah, so remember the counterclockwise pattern? So you start from the pointer and you work your way around in a spiral fashion. So you start with a pointer and you see, oh, you encounter a const right here. So it's a constant pointer to is it a constant int or just a normal int? A normal int, okay. So the pointer itself is constant, but the value of what I'm pointing to is not constant. So am I changing here the value of what I'm pointing to or the pointer address?
You're trying to change the address.
Trying to change the address. So is there an error here? Yes. Because the pointer I'm saying here is constant, but here I'm trying to change the pointer. What if instead on this line right here I said star pointer plus plus? Would that be okay? Yeah, because I'm trying to change the value, but that's not const. And so that would be okay. So, but in this case, there is an error, and the reason is that the pointer is const. So going back to algorithms on the searches, linear and binary search. So linear search, remember big O notation is roughly how long the algorithm takes in the worst case. So linear search takes O of n time because I may have to search the entire list, and binary search takes log n time. So I kind of gave away the answer for linear search. You have to search the entire list. Why is binary search log n here?
On average, you can eliminate half of the values with
Yeah.
each iteration.
Yeah, so not even on average. In every case, I cut the list in half. So we worked out several lectures ago that because we're cutting the list in half every time, we can achieve log n performance. So that's the reason why binary search takes log n time. So this one's actually kind of a hard question. Hardest of the 10, I think. Suppose that we have a set of student objects, doesn't have to be students, but we're sorting them by a specific attribute, say first name. And now I want to sort it, this list of students by last name, but keep the first name order the same. So I don't want to have to, so I sort by first name, but I don't want to muck up the order with the first name that I've already done. But I want to have it in last name order. So what are the algorithms that we talked about that sort things at all? Bubble and selection sort. Do they guarantee this? No. So in fact, which sorting algorithms help accomplish this? Neither. So what this question should hint to you at is that you need different types of sorting algorithms for different problems. So if I want to have this type of sort, then I need a different type of sorting algorithm. So, and by the way, if you're curious, this type of sort is called stable sort. So the first sort that I did, it's stable under the new sort that I'm doing. So there is an algorithm in the standard library called stable sort. So there is a way to do this, but the sorting algorithms we learned, there is no way. I think so. Yeah. So yeah, you don't have to know what gather does, but yeah, there is a function like that. So this is kind of related for question 10. This is kind of related to what we did before. So what's the error here?
Trying to return by reference.
We're trying to return a variable by reference. Yeah. So that's the issue with that function. So remember, all 10 of these questions appeared on the previous final. So these are the types of questions that I will be asking. Okay, so are there any questions on these? Or anything else on the final, or anything in the class, or anything else? Someone, anything. Are you alive out there? Is there anybody out there? That's for you Pink Floyd fans out there. Okay. Okay, so let's continue from where we left off. So what were we talking about last time? Making classes useful. So in particular, what thing about classes were we talking about? Yeah, overloading operators, we talked about that. And what else have we talked about? Copy constructor. So what is the purpose of a copy constructor? Or what does it take as an argument? Yeah. Yeah, so if we're making a class like CP class, the copy constructor takes exactly one other argument, which is another object of the same type. So the example we had here is we're making a constructor. So it's just a normal constructor, but it just has a different name. And then we're taking an object of the same type as its argument. So I'm passing a CP class object here, and so it's a copy constructor. So by the way, why is this object here passed by const reference? Yeah, we don't want to modify the original. So why don't I just say pass by ignore the reference and ignore the const? So this will do a copy, but what's the issue here?
You're making a redundant.
I'm making a redundant copy. So we don't want to make redundant copies. I want to make a copy, but not redundant ones. So here, I do want to pass by reference, but because it's a copy, I don't want to modify the original. So we put const on it. By the way, do I have to put const ref here? No, but so is this a convention? Yeah, so get used to the conventions here. Then we talked about operator overloading. And so what is the nice thing about operator overloading?
You can make the operators essentially do whatever you want.
Yeah, so we can make certain operators do whatever we want. So like, remember smart pointers, overload the star operator to make them behave like normal pointers. So we don't have to call some obscure function. We can just work with it like a normal pointer. Or vector, for example, overloads the square bracket so that we can make it look like a normal array and have it interact like a normal array instead of calling some other function. So the way you do it is whatever operator you want to overload, the name of the function literally is operator, the operator. And then depending on what you're designing the operator for, you could have no arguments here, or you can have one other argument or something. And then you return here the thing that you want to return. So in the case of matrices, for example, if I'm overloading an operator plus, which is a matrix plus another matrix, what should the return type be in that case? Matrix. So the return type can be anything, but it has to make sense for what you're actually doing here. Yeah, so we could have an overloaded plus operator here, and what you do inside is you create an object of whatever you want to return. So if we're adding two OP classes or two matrices, make a matrix on the inside, do whatever addition you actually need to do on the inside, and then return the object. It's really simple to do this. And then in code, all we need to do is just say A plus B instead of having to call a function. You could do that, but it's definitely a lot easier to do this. Okay, so some other operators. Let's dive into this. So we can overload assignment operators too. So we could have an object on one side and a different object on a different side, maybe, and then we can have the assignment do whatever we need to do. So we've actually been using this since the very beginning of the class, and you may not know it. So let's go back to this example, hello world. Simple example here. So what is the type of the thing on the right side? Is it a string?
No.
No, so what is it? Does anyone remember? Yeah, const char starts with a point and ends in an Pointer. Okay, so the type of the thing on right-hand side is const char star. So it's a pointer to a const char. So a constant, so you can think of this as just an array of characters that can't be modified. That's another way to think of it. But is a string the same thing as a pointer?
No.
No. So what is happening here? So string overloads the assignment operator to say, so somewhere buried deep in the class string, so this is not the actual implementation of string, but in here somewhere, we have, well, let's see. So I want to convert this const char star to what? What am I converting it to? String. So the operator for assignment should return a string. So here I'm returning a string, and I'm overloading operator equals because I'm overloading the single equals, which is assignment. And the thing that I'm passing in is a const char star. Let's see the, maybe we'll call it right-hand side to make it similar. And then in here somewhere, we're converting a right-hand side to a string and then return the string. So obviously this is not the real implementation, but what's happening here is that string is overloading the assignment operator to make programming easier. We don't have to convert the thing on the right side to a string first and then assign. it's a lot easier to just say, put the not actually a string thing on the right side, and then just use the assignment operator. Much easier to deal with. So overloading the assignment operator, you can put anything you want on the right side. I could have multiple operator pluses here. I could have an integer over here, and I could have an integer be converted to a string if I wanted to define that operation. Okay? So we can define any type of operation we want. We can just say the equals, we can convert from this to this, anything we want, which is extraordinarily powerful. So to just recap, so let's just say that we have a custom class right here, so a constructor here, a destructor, and here we have an overloaded assignment operator. So here, what is the type of the thing on the right side of the assignment operator here? Yeah, another CP class. So in this case, the only way we could assign to a CP class object is with another CP class object. But we can define another one to convert from, say, well, we have an integer pointer right here. Convert from an integer pointer to a CP class. That'd be another way to go. Or convert from just a normal int over. We can do pretty much anything that we want here. Yeah, so we can define it possibly this way. So let's say we're taking a CP class other argument, and we want to assign it to ourselves. So we're taking the pointer inside the CP class object, the one that we're passing in, and assigning it to our own pointer. So we're just copying the value in this pointer to ourselves, and don't worry about this at the end here. That's actually something that's kind of interesting. So one of the issues with this, with operator overloading here, is sometimes you create a string S like this, and then you do stuff and you return S. So the issue is that is this S the same as the current string? Or are we making this string inside the function? So is this string right here the same as the object that we're making of type string? No, it's not the same object. So here what they're doing is we're returning ourselves from the function. Don't worry about what it actually does. It's just to avoid having to create an additional object here. So the upshot of all of this is, suppose we have two CP class objects, we can just say A equals X, like this. So we can just assign like this. So we can do the same thing with matrices, with vectors, with strings. We can just put an equals there and copy all the contents if we need to, which is really, really awesome. Okay, so some overloading things. So the word overloading just means we're changing the behavior of something. So we're redefining the equals operator for assignment. So that's overloading the equals, the assignment operator. We're just changing the behavior of whatever it is. So the overloaded operator, which is really interesting, if you have the operator as public, even if you have private data members, the operator has access to the private data members, which is kind of interesting. So even if they're private, so you can't access them directly in any other function, you can access them with the overloaded operator. But it has to be inside the class for that to work. If you put it outside the class, then you have to do something special, something called friending the class. It's not Facebook, but you have to friend the class first. Don't worry about what that actually is. Yeah, so overloading, of course, can change the entire meaning of what an operator is. So plus before can mean whatever we want to. Whereas before, with, say, integers, it means a specific operation. But could I say a string plus another string? What does that do with strings? It puts them together. Is that adding the two strings? Not in the sense of integers. So we can define the operators can mean completely different things. So you have to be crystal clear if you're overloading operators, what it actually does. So if you define it to mean some custom thing, then you may not know exactly, if someone's using your code, they may not know exactly what is going on.
So if there are conflicts between like the header-based definitions of the operators and like a personal one, does it defer to like the default ones or does it defer to the user-defined ones?
What do you mean by conflict?
Like, so if you tried to set an operator that conflicted with like the behavior of, I'm trying to think of an example.
Okay, so what you're saying is, if I try to overload an operator and it conflicts with like all of C++ essentially, would there be an error? There's actually a big list of which operators you can overload. So like you can overload all of the comparison ones, like bigger, less than, equal, double equal, not, square bracket, pointer. There are a gazillion operators you can overload. Let's actually look because I don't know. Let's see. So operators C++ can overload. Let's see. There should be a gigantic list somewhere. Let's see. So all of these operators you can overload, all of them. So I can overload plus, minus, times, divide, percent, the caret. So there are many different operators you can overload, even ones we never even talked about, which are these. So we can overload new and delete. So be careful. So like with new and delete, the programmer knows or should know exactly what those operators do, because new is supposed to mean dynamically create this object. But if you define it to mean something else, then they may not know your behavior. Whereas if you have overloaded plus with matrices, that has a really specific meaning. So just be very careful if you're overloading operators, which ones you're overloading. Yeah, so here's actually a really interesting one. At least to me it is. So you can overload parentheses. So if you create an object, so like a CP class called C, I can call C parens and make it look like a function, even though it isn't, which is really weird. So just be careful in trying to make it more readable instead of less readable. Yeah.
So when operators overloaded in the class, can it only be used in the class?
I don't know what you mean by only used in class.
Let's say you allocate plus to mean something else.
Yeah.
You use it outside of the class. Would it still mean addition or would it
Yeah. So like in this case, so like remember, string has the overloaded plus to mean put the two strings together. So if I have S2 is CSE100, I can see out S plus S2, for example. So this is outside the class. I think what you're trying to ask is, could I have the plus be used in a different context? So like instead of just two strings, in another statement I can have two integers added together. And so the plus in both cases has a different meaning. Is that what you're asking? Okay, so that's one of the really hard things about building compilers, is that if I do something like this, are these two statements the same operation with plus? No. So the compiler has to figure out what exactly does this plus mean. It has to unambiguously figure out what that means. Because if there's ambiguity, like it could do this or this, then it can't figure out what to do. So it has to figure out, okay, this plus is taking a string and another string, and this plus is taking an int and another int. So that's one of the hard things about compilers. But you can use the plus in any context, or really any operator in any context, as long as it makes sense in that context. Other questions? Okay, so prepare to have your mind warped. You thought we were done with references. We are not done with references. There's more referencey goodness to come. Okay, so we've only actually heard about, I think, 1/4 of all types of references in C++. Thankfully, we're only going to introduce ourselves to one other type of reference. And maybe one more. We'll see. So let's see. So the concept is actually really, really simple, but it can be misunderstood quite easily. So the references that we have been talking about so far, where we just have one ampersand, those are called L-value references. So left value references. So the reference we're going to talk about next is called an R-value reference, or right value reference. And so what's the difference? So an R-value reference is just something that is just a fixed value. So if I take something like this, so if I say an integer x equals 100, 100 itself, the actual number 100, that is an R-value reference. Or it really is an R-value, and the reference is, if I have a reference to that thing, that is an R-value reference. So the thing that goes on the right side of the assignment, those things in general are R-value references. Okay? Whereas X, if I print it out, say the reference corresponding to X, is this an L-value reference? Yes. So here's the rule in which one is which. If you can take the address of something, it's an L value. If you can take the address of something, it's an L value. Everything else is an R value. Okay? So can I take the address of 100? No. So is it an L value or an R value reference? R value reference. Any questions on the difference between the two? If you can take the address, it's L value. Otherwise, it's an R value. Yeah, so we've actually been using this since the very first day. So if you have something that's like a fixed value like this, or for example, we make a character and it's just a single character over here, that is also an R value. And the reference corresponding to it is an R value reference. So how do I make a reference to this? So an R value reference is just a reference to an R value. That's all it is. If I wanted a reference to an L value, I just make an L value reference with a single ampersand. Whereas if I want an R value reference, it's 2 ampersands. Okay, so POW 3.02, which is obviously 9.0, that thing is an R value reference because I can't take the address of it. So it's an R value. So if I want to make a reference to it, I need to make an R value reference. So the thing on the right side is an R value. The thing on the left is an R value reference because it's a reference to an R value. And then if we print this, it'll print the reference here. So the reason why there's a difference here is that the R value reference is technically a temporary location. So it's not a variable that you can just assign everywhere. So this is just a fixed value. You can't move the address around or anything. You can copy from it, but you can't really do anything else with it. So yeah. So declaring the R value reference assigns a name to the temporary location holding the value of the expression. So this R value is a temporary location, and when I assign it to a variable, the variable now, can I take the address of this variable right here? It's a variable name. Can I take the reference of a variable name? Ignore the reference on it. If it's a variable, can I take the address of it? Yeah. So now it's an L value reference. But the reason why we have the ampersands here is that to demonstrate that this is an R value reference on the right side, but I'm creating an L value reference here. So this is kind of pointless right here. We'll see why R value references are important. But here, I'm just showing you that the thing on the right side, if I want to make any reference to it at all, it must be an R value reference. Any questions on what an R value reference actually is? Oh, by the way, here's a question. So let's go back to the example that we had a while ago. Let's see. Keep going, keep going. So let's just say we had this horrible example where we're trying to return a local variable by reference. What if I try to return it by R value reference? I'm going to emphasize a word. We're returning it by R value reference. Yeah. Yeah. So an R value reference is still a reference, and so it still has the same issue. So sometimes you'll actually see this in code, like you're trying to return by a reference. It's not a good idea. So you may think, okay, this seems kind of stupid, right? We can just deal with variables and just deal with their references all we want. Why do we need R value references? So here's the issue. So suppose that we had a string f, and maybe this. Okay, yeah. So let's do it this way. So let's do operator plus. Let's implement operator plus, which means what for string? What are we trying to do with the plus operator? Change its behavior. So what is the common operation between a string plus something else? What usually goes there? Something else is usually a string, right? So let's pass in a string, s, and then maybe let's call it other. And then let's do this. So let's just say that we're going to make a string which is corresponding to hello and other. So we're passing some string in, putting hello on the front of it, and returning it. Any questions on what this code does? So what if this other string is incredibly long? What could we do to make this faster? Pass by reference, so that we don't make a copy, right? Anything wrong with this? No, it seems okay. So what we can do is, let's just say that we have a string s, which is world, and then we see out, yeah. So let's do, I'm actually going to rename this to something else so that we can actually see it in action. So let's call it f. So then I can say f of s, and that's it. So what this does is we create a string here, pass it in, so it becomes this other string. We put hello on the front of it, return it, and then we print hello world. Okay, any questions on what this actually does? Okay, what, sorry?
There's not going to be a space in it.
Well, okay, fine. I'll cater to your demands. Okay, so here's what I wanted to actually show you. Is other, the actual word other in this function, a name of a variable? Yeah, it's the name of a variable. Can I take the address of it?
Well, in the scope of the...
Yeah, in the function. Can I take the address of it?
Yes.
Yeah. So, so what does that make it, an L value reference or an R value reference? L value. Cool. So let's try to pass in a R value reference in. Is this a sensible thing that I want to be able to do? Should I be able to do this?
Well, yes.
Yeah. Or even this. So let's actually do it with ints to make it even more clear. So let's just make a function called square, which just takes an integer reference n, and all it does is returns n times n. So if I make an integer x equals 100, then I pass in x, there's nothing wrong with that. But what if I pass in an R-value reference in?
Yeah, that's fine.
Why? No, it isn't. Can I take the address of 100?
Oh, no, you can't.
I can't. So because n is an L-value reference, this seems to say that square, the function square, can only take things by L-value reference. So I can only pass in a variable, the name of a variable. Whereas this seems like a logical thing to do, like be able to pass in an R-value reference. So then you may say, well, okay, well, I want to be able to pass R-value references in. I should be able to put a R-value reference on this thing. Well, this actually isn't an issue, but is there an issue now? Yeah, it seems like it only takes R-value references, right? So it seems like, is this going to be an error if I try to pass x in? Remember, what is x? Is it an L or an R value reference?
No.
It's an L value. So that means that it seems like this won't work, because it seems this function says I take R value references. Here's the great thing about C++. This will work. So let's see, do we have time? Yeah, we do. So one of the really weird things about this is that we never encounter double ampersand other than inside the parameter list of a function like this. So why do we put this here? What happens here is that there's a special rule that says that if you have a double ampersand on a parameter like n here, it can bind, as it's called, to L values and R values. So if you pass an L value in, it'll work. If you pass an R value in, it'll also work. Yeah.
I know this wouldn't be by reference, but if you took both ampersands away, it would still work, right? It would just sit in the
But it'll make a copy.
Yeah, but
It would still work.
with both, right?
Yeah. So yeah, this will, as was pointed out, this would work. But in some cases, I do need to pass by reference, or I should pass by reference. And if I only leave one on there, that'll throw away any R value references. So this is something called a universal reference. And I'm not sure if that's in the slides, and I won't test you on it, but it's just you'll see this term more often than, like, say, L value and R value references. Because here, we want to not have to do this. I don't want to have to write this code, where I have one version which takes a single ampersand and one other one which takes a double ampersand. So here, the great thing is that you don't have to. You can just write one function, which is nice. So here, I can pass in a variable, or I can pass in R value, and everything will work fine. Yeah.
Wouldn't you just make it double, like universal reference for pretty much everything?
Right, so that's one of the things about C++'s library. A lot of the things are universal references in there. Mm-hmm. Yeah, so yeah, to avoid unnecessary copies. Yeah, so most things as parameters are universal references. Yes.
So have we basically been passing everything by a R reference this whole time, because we're just passing it over?
So you mean by this?
Yeah, well, like without a reference on it at all.
So
Basically
so
passing it by R.
so remember, those are passed by value. So it's making a copy.
Yeah.
Whereas when we had one ampersand here, that's passing by L value reference.
I guess I'm just confused with how it makes a copy of just the number without it having like a.
It's a separate location in memory. So it's still making a copy. So for integers, it's not really a big deal, because the amount of time it takes to make a copy versus just pass the reference along, it takes the same amount of time, so it doesn't really matter. But for larger objects like string or vector, you want to pass by reference, but sometimes I want to pass by R value, so something that you can't take the address of. Whereas if we just leave it like this, then I can't pass anything that is an R-value reference. So that's why we have a double ampersand here. Okay, any questions about this? Because we're going to get to something pretty important. Okay, so we talked about the copy constructor. So what does the copy constructor do? It makes a copy, right? So we have some object here, and I want to make a complete independent copy here. So remember unique pointer. So what was unique pointer?
The pointer that can only have one thing associated.
Right. So we have, or even the object has one pointer associated with it. Yeah. So we have some resource, and a unique pointer says, if I'm pointing to this thing, no one else is pointing to it. Okay? Well, what if I want to change ownership of this unique pointer? What do I have to do with the ownership of that object? Could I copy it to some other unique pointer, or do I have to move it to another unique pointer? I have to move it. So you may think, okay, well, if we have to do that, how do I make the new unique pointer from the old one? Well, we can't do a copy constructor on it because I can't make I can't have two things pointing to this thing because it is a unique pointer. So this is where the move constructor comes in. So the idea is formal terminology coming to you. I have an object here, and I want to take all of the guts out of this object and move them to a complete different object. So I never have two independent copies at any point. So I'm taking all the guts out of this one, and I'm moving them over here. I'm ripping the heart out of it, and I'm transplanting it into a new patient. Okay? So, yeah. So copy assignments and copy constructors, blah, 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 blah. So copy assignments, importantly, are resource intensive because I'm making a copy. But sometimes you have to do that. For move constructors, we're not making any copy. Okay? So the reason why we introduced R-value references is that we need R-value references for a move constructor. So they're much more efficient because I don't have to make a copy anymore. So when would this actually be useful? So how does vector work? So we are doing pushbacks into a vector, and at some point, what happens? So it has an internal data storage, some array somewhere. What happens? Let's just say the internal storage becomes full. What happens?
It would move it somewhere else.
We'll get to that. So let's just say that, so let's just say we have this. So we have a vector right here, which has the values 5, 10, and 13, let's just say. And let's say that this is the internal storage of vector. It's the internal storage. And so it has size 3, and I'm going to call pushback. So we're going to call pushback of, say, 42. Well, what has to happen here? Well, let's see. Is the internal storage full? Yeah, it's full. So what do I have to do? I have to make a new one. So what usually happens is that we double the size of the internal storage. And yeah, so we double the internal storage. So let's just say we do this. And so the naive implementation says, okay, I'm going to just copy all of the original elements from the original storage to the new storage. I'm going to copy them. And then when I'm done copying them, I destroy the original vector. The original data storage here. So I'm copying everything from a thing of size 3 to a thing of size 6. And then after that, deleting the thing of size 3. So in this case, I'm going to move 5 over, then 10, then 13. And then, because I called pushback, I'm going to put 42 after this. And then this obviously is not a full container anymore. So what is the issue with this idea? It's resource intensive, right? Because we're making a copy of the object. So what if these were strings in here? An arbitrarily big string. Well, what's the issue? If we're going to copy everything to the new data storage, then I'm going to have a duplicate of these first three, and then hello in here, and then some other stuff. So here, what is the issue? Right, I'm making this much more resource intensive than I need to. What could be better? Well, let's see. Once I take these three strings out of this original data storage, do I need them anymore? No. So what can I do instead? I could move them instead. Instead of copying them over to the new storage, I move them. I don't have to make any additional copy. Doesn't that just give you goosebumps? It gives me goosebumps. Isn't that just so cool that we could just move everything over, and then I'll talk more about this Wednesday.